on, dear students. In the previous class, we derived the transformation matrix L. The transformation matrix L is a 2 by 4 matrix. How it was obtained? L equals to a 2 by 4 matrix having the elements L, M, 0, 0, 0, 0, L, M. Okay? This is the transverse matrix. What are small l and small m? We use small l and small m to denote direction cosines. What is small l? It is cos theta. It is cos theta. Small l is cos theta. What is small m? Cos phi, where phi is 90 minus theta. Remember, phi equals to 90 minus theta. Therefore, you get sin theta. Where L and M are the direction cosines. How you determine that is the question. Now, here we have a truss element of length LE. Theta is the orientation. The truss member is inclined at an angle theta with the horizon. Right? This is node 1 and this is node 2. Where the nodes are taken in truss elements? At the ends. Nodes are taken at the joints in the truss structure. Okay? Because we consider here two-dimensional truss structure, each node is specified by two coordinates, two Cartesian coordinates. Let x1 and y1 be the Cartesian coordinates of node 1 and x2, y2 be the Cartesian coordinates of node 2. Okay? Now, right? Now, what is the horizontal distance between nodes 1 and 2? It is simply x2 minus x1. And the vertical distance between the nodes 1 and 2 is y2 minus y. Okay? Now, here the direction cosine L, which is simply cos theta. Now, if you observe, this is a right angle triangle. Okay? Hence, cos theta equals to x2 minus x1 by length of the element. We are having here. Next, direction cosine M. M equals to cos phi. Phi equals to 90 minus theta. Which equals to y2 minus y1 by length of the element we are having here. Cos phi equals to sin phi. Understand? Now here, LE is unknown, but we have the coordinate positions of both nodes 1 and 2. Both nodes 1 and 2 with respect to the global reference frame. With respect to the global reference frame. Remember, we have the coordinate positions of nodes 1 and 2 with respect to global reference frame. But length of the element we want. So length of the element, we can determine using this formula. LE equals to square root of x2 minus x1 whole square plus y2 minus y1 whole square. Right? So first you have to determine length of the element. Right? And you have the coordinate positions of the nodes. Therefore, finally you can determine the direction cosines L and M. When you determine the direction cosines L and M, you get the transformation matrix L of size 2 by 4. Remember. Okay. Now, once you determine the transformation matrix, you can determine the element stiffness matrix. Okay. We know that for a two-noded bar element, the element stiffness matrix K equals to EA by L into a 2 by 2 matrix having elements 1, minus 1, minus 1, plus 1. E is the Young's modulus. A is the cross-sectional area of the element, right? It is an element of uniform cross-section. And L is the length of the element. Here the subscript E is used for element. Okay? EE, AE by LE into a 2 by 2 matrix with elements 1, minus 1, minus 1, plus 1. Okay? Right. Now, the truss elements of the structure have different orientations. Therefore, each node of the truss element has 2 degrees of freedom. 2 degrees of freedom with respect to the global reference frame OXY. With respect to the global reference frame OXY. Right? If this is element 1, node 1 has 2 degrees of freedom, Q1 and Q2. I told you, if I denotes the node, right, the displacement in the direction of x-axis is denoted by Q to I minus 1 and the displacement in the direction of y-axis is denoted by Q to I. Accordingly, I have specified. Next, this is node 2. Therefore, this is the displacement Q3 and this is the displacement Q4. Okay. With respect to the global reference frame OXY, if you prepare the element stiffness matrix, right? The size of element stiffness matrix for the truss element with respect to global reference frame, we get 4 by 4. Because at each node there are 2 degrees of freedom. We know that the size of the element stiffness matrix equals the total degrees of freedom of the element. The size of element stiffness matrix equals the total degrees of freedom of the element. How many degrees of freedom are there? 1, 2, 3, 4. Therefore, here, with respect to global reference frame, we get the element stiffness matrix with size 4 by 4. This we need to derive. Okay? Next. For each truss element, we take a local reference frame. Therefore, for this element, I can take a local reference frame like this with x dash axis and origin here. With respect to this local reference frame, tell me how many degrees of freedom this element has? This element has 2 degrees of freedom. What are they? Tell me. Say Q1 dash and Q2 dash. With respect to local reference frame x dash, this element has 2 degrees of freedom. Right? At 1 and 2. What are they? Q1 dash and Q2 dash. Therefore, here, with respect to local reference frame x dash, the behavior of this element, if I observe, it appears as a 2-noded bar element. Therefore, for which I can express the element strain energy like this. The element strain energy UE equals to 1 by 2 Q dash transpose into K into Q dash. Remember, this is the expression for element strain energy written with respect to the local reference frame x dash. Because the behavior of this element with respect to local reference frame is appearing as the behavior of a 2-noded line element, 2-noded bar element. Therefore, I write like this. Right now, the element strain energy equals half into what is Q dash transpose, right? Now, to write Q dash transpose, you must see what is Q dash. We know that Q dash equals to LQ. L is the transformation matrix and Q is the element displacement vector. Understand? Element displacement vector. Therefore, Q dash transpose equals to Q transpose into L transpose. Q dash transpose equals to LQ whole transpose. Hence, you can write Q transpose into L transpose. Hence, we have written here Q transpose into L transpose into again. Now here K into in place of Q dash I write in place of Q dash I write LQ. In place of Q dash I write LQ. Understand? Now, if we express this right as say half into Q transpose into some term in brackets into Q like this. Right? Why you write? Because this is the usual form to represent element strain energy in terms of element displacements and element stiffness. Element displacements and element stiffness. This is usual form. Hence, if I compare this form with this, now what is K here? K equals to L transpose into K dash into L. Dash is missing here. Put dash. It is missing here. Put dash. K dash. Okay? Now if you compare these two, what is K here? K equals to L transpose into K dash into L. Understand? Right. Where K is the element stiffness matrix in global coordinates. What are they? X and Y. Where K is representing the element stiffness matrix in global coordinates X and Y. Therefore, you get the element stiffness matrix K with respect to global reference frame in size 4 by 4. That we see. Here, so K equals L transpose K dash L. So we have L transpose. In fact, L is a transformation matrix of size 2 by 4 with elements L, M, 0, 0, 0, 0, L, M. Okay? Now L transpose, size of L transpose, tell me how much? Size of L transpose is 4 by 2. And size of K dash, it is 2 by 2. And size of L, it is 2 by 4. Now, the resultant matrix, contains the size 4 by 4. Therefore, if you multiply L transpose with K dash, then K dash with L, you get a matrix like this for element stiffness of the truss element with respect to global reference frame. K equals to EAE by LE into a 4 by 4 matrix. Right? Now these elements, if you observe, they correspond to the first, second, third and fourth degrees of freedom. Right? First, second, third and fourth degrees of freedom. Understand? So this we have to remember. How we get? We can determine this element stiffness matrix with respect to global reference frame. After calculating the direction cosines L and M. Understand? Right. Remember here it is LE is length of the element. Here LE is the direction cosine. Be careful. Next. Once you determine the element stiffness matrix, small k, you can also determine the stress in each truss element. Stress in each truss element. Right? In each truss element. How? Once you determine for each truss element, once you determine for each truss element the element stiffness matrix, all element stiffness matrices you have to assemble for global stiffness matrix. For global stiffness matrix, if there are three element stiffness matrix you have to determine. Then assemble, you get global stiffness matrix. Right? And in truss structures, we observe the concentrated forces acting at the joints. Then you prepare the global load vector F. Right? And you write the equations of equilibrium. Capital K into capital Q equals to F. If there are n degrees of freedom in the truss structure, the size of K is n by n. Then what is the size of Q? N by 1. What is the size of F? N by 1. Okay. Impose the boundary conditions. Impose the boundary conditions. For example, I take a simple truss like this. This is a simple truss. How many elements are there? One element, two element, element 2, this is first element, second element, this is third. Understand? Now, I say this is node 1, this is node 2, this is node 3. Now the displacements at each node, observe carefully. Now here, the displacements at each node I represent, observe carefully. This is capital Q1, this is capital Q, capital Q3, capital Q4, capital Q5 and capital Q6. Here the displacements at nodes 1 and 3 are known because Q1 equals to 0, Q2 equals to 0, Q5 equals to 0 and Q6 equals to 0 because nodes 1 and 3 are fixed. This node 1 cannot, the point 1 cannot move horizontally, it cannot move vertically. Similarly, node 3 cannot move horizontally and vertically. How many specified displacements are there? 4. Okay. Once you write the equations of equilibrium like this, substitute these values. Understand? And solve. You get the remaining degrees of freedom. Okay. Then determine stresses in the elements. How we determine using the formula sigma equal to E into epsilon. Sigma equals to, we know that epsilon equals to B into Q. Epsilon equals to B into Q. That is what I have written here. What is B? It is simply 1 by length of the element into a row matrix with elements -1 and +1. Right? And Q, for first element, it is a column matrix having the elements Q1 and Q2, like this. Understand? Right. So, stress in the element we can determine. Stress in the element we can determine. Understand? Right. Once you determine the stress in the element, you can also determine strain in the element also. Okay. Here, observe carefully, Q1 and Q2 are the nodal displacements with respect to global reference frame. These Q1 and Q2 you do not get directly. How you get? You have to transform, the local displacements to global displacements. Q1 and Q2 are the nodal displacements with respect to global reference frame. Right? How you get? After transforming the nodal displacements defined with respect to local reference frame to global reference frame. That we see here. So sigma equals to E into Q2 dash minus Q1 dash by LE, which equals to EE by LE into, right? Strain displacement matrix, minus 1, 1 into Q1 dash, Q2 dash. Because here E equals, right, epsilon equals to B into Q dash. With respect, epsilon equals to B into Q dash with respect to local reference frame. Here, epsilon equals to BQ, this is with respect to global reference frame. What is Q here? A column matrix having the elements Q1, Q2. What is Q dash here? A column matrix having the elements Q1 dash and Q2 dash. Right? This is the relation pertaining to global reference frame, and this is the relation pertaining to local reference frame. Here, stress in the element is represented, the expression for stress in the element is represented with respect to local reference frame. Therefore, sigma equals E into Q2 dash minus Q1 dash by LE, which equals to E by LE into a row matrix with the elements minus 1 and 1 into a column matrix having the elements Q1 dash and Q2 dash. Right? This is the matrix representing Q dash. But we know that Q dash equals to LQ. Okay? Then what you get? That we see. Q dash equals to LQ. So stress in the truss element equals to E by LE into a row matrix with the elements minus 1 and plus 1 into L. Write the transformation matrix. Okay? Then multiply it by the displacements of the vector Q. What are the displacements? Q1, Q2, Q3 and Q4. Right? These are the elements of the displacement vector defined with respect to global reference frame OXY. Now, so when you multiply, you get stress in the truss element sigma equals to E by LE into a row matrix with elements minus L, minus M, L, M into element displacement vector Q of size 4 by 1, remember, of size 4 by 1. Right? Size of this is 1. Once you determine stress in the element, you can also determine strain in the element. Okay? And later you can also determine the reactions at the supports. Okay? Right? Thank you. Thank you.